This video talks about gravitational force. There's only one formula for gravitational force. However, it does play a huge part with circular motion. So we need to go back to our circular motion formulas, and we know that circular motion force, or centripetal force, is equal to mass times velocity squared over the radius. And this will come in handy later on. The gravitational force formula, on the other hand, is a little lengthy, but it's pretty easy. So we have our gravitational force is equal to the gravitational constant g times mass 1, mass 2 over the distance between them squared. And sometimes they'll use radius instead of distance. Those are interchangeable as well. The gravitational constant is a constant, so it is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Capital N, sorry. Newton meters squared per kilogram squared. So when we plug this into the formula, the meters cancel with the distance squared, and the kilogram squared cancel with the mass squared. So there's easy concepts that go along with gravitational force, and usually gravitational force is referring to large celestial bodies. So we're talking about planets here. So here we have the sun. I know it's not very sun-like. There you go. It's a little bit yellow. And then we have, let's say, Mars out here. Mars is a lot smaller than the sun, as most planets are, but they both exert equal but opposite forces on each other. This is what we call the gravitational force, and we actually exert the same amount of force on the Earth as the Earth exerts on us. We don't make as much of an impact on the Earth as the Earth does on us, though, because our mass is so small. So when we talk about planetary, this is where they actually affect each other a little bit more. We know that Mars rotates around the sun, much like Earth does, in a circular orbit. Well, it's not really circular, it's more elliptical, and we'll talk about ellipticals in the next video. So here we have Mars, and it's being attracted to the sun, and the sun is also being attracted to Mars at the same force. All we have to do is determine the distance between the two. The centers is usually where we determine those from. And this is either our radius or distance. And then we just plug all that in. So the mass of the sun and the mass of the Mars, we plug these in for M1 and M2. And then we square our radius. As the planets move farther away, so let's say now we're talking about a planet in another galaxy that is very similar to ours, that maybe the mass is bigger, but the radius is the same. So if the mass of an object gets bigger, then that has a direct relationship with the force between the two objects. If the mass gets smaller, then it has an indirect relationship with the force of gravity. So that's pretty easy to understand. The bigger the planet, the more gravitational force it has. Jupiter has a huge gravitational force, even though it is mostly gas because of its giant mass. And we still have our mass the same as when we were on Earth. Now, the farther away an object gets, the less the force of gravity is. And that gravitational force decreases exponentially. And the reason it decreases exponentially is because of this square root right here on the distance. So let's say that we took this planet and we moved it 3 times farther from the sun. When we do that, we just plug in the 3 down here, and instead of being divided by 3, it's now divided, or by 1, it's now divided by 9. So the gravitational force at this point is 1/9 of the original because our masses don't change, neither does our gravitational constant. So it's really important to understand that the farther away it goes, the much less that gravitational force is because of the squared aspect of the distance. But as the masses increase or decrease, it has a direct relationship with that gravitational force.